Welcome back. Before we present examples of equivariant degrees for certain linear maps, for let's say like this, examples of basic degrees, we need to discuss a concept of the character of a representation. So let me write simply what is the topic for this lecture. So this is character of a representation. And let me begin. So let's say, given a compactly group, group G and an orthogonal G representation and I call it V. Suppose that's exactly Rn, so we have here orthonormal basis, which gives us an isomorphism with the Euclidean space. So, in other words, we also have for this particular representation, there is the homomorphism. This is a smooth homomorphism that goes to the On. So, by the definition, G applied on a vector x in V will be just simply Gx. Then here is the x belongs to V, and of course G belongs to G. So this can be seen here, this homomorphism is basically the way how to describe the action of G on this Rn. So in such a case we can define something which will be called the character of this representation V. So let's say like this, by a character, write it down, character. And I put the Greek letter V of the representation V, we mean the function and this will be V that is defined on G, and it takes the real values, and in this case this CV on any element G belonging to G, by the definition this will be the trace of the matrix T of G. So this is the trace of the matrix G. So remind, so this is G belongs to G. So let me recall, so if you have here a matrix, the matrix is Aij, that's a square matrix, so this is just equal A11 plus A22 plus A and N. So this is the trace of a matrix. So since the trace in our case will be, let's say, has certain properties, so let us, maybe you should say like this, as a conjugacy sequence, as a direct consequence of the definition of the of the properties of the trace, we have that first of all, that put it like this, number one, that for any for any age belonging to G and for any G belonging to G, the character of V, which will be written like this, H, G, and I put here H minus 1, this will be the same as character of V on H. Character on V of H. And here, why? Because that's exactly the property that is satisfied by the trace. Yeah. So in other words, therefore, maybe like this, therefore, the character CV is a function constant, which is constant on the conjugacy classes of elements G belonging to G. So what is the conjugacy class? So let's write it down. The conjugacy class of an element will be just set of all G prime such that G prime is equal to, and put it like this, H, G, H minus 1, and here is for some H belonging to G. So those are the conjugacy classes. So in such a case, we can say like this, if, so that means if G, let's say like this, C conjugacy classes. So maybe let me write it down in red so it will be clear. So I write it down. C and C conjugacy classes of the group G. So maybe continue with red, of the group G. So this would be equal by the definition, the set exactly of this conjugacy G such that G belongs to G. Then character actually is a function which is defined. Then character so V is actually the function, well-defined function on these classes. And you can write it down. V, it goes from CCG to R. CCG to R, so that is the same. So maybe let's look at an example. Why not? Let's look at an example. So let's take, for example, Always good idea to have an example. And I would say, let's take G is equal, not dihedral group, D5. So in such a case, we know what it is. This is 1, complex number gamma. Maybe I should not put this. It's just not a big deal to write all of them. So 2, 3, and 4. And then we have kappa, gamma, and okay, kappa, maybe other ways. Gamma kappa, gamma square kappa, gamma cube kappa, and gamma 4 kappa. Where gamma is just this EI 2 pi divided by 5. So that's this complex number. And now let's define the natural, consider the natural natural D5 representation which will be in our case the V will be equal R2 and this will be C. So in this case we'll know that those are the rotations, and those are the reflection. So where D5 acts by multiplication, by, let's say like this, complex multiplication. For G equals rotation, for G being rotation, so put it like this, J, and kappa on Z is equal to Z bar. So we were discussing this type of the representations earlier. We were discussing this. So let's find out what is the character of this representation. And it is not difficult to see, so this is my representation V, and here we have here 0, and of course this is D5, so you can let me make a little circle, so we know those are the rotations that are related to a pentagon. So I have here pentagon, this is 2, and there are 2 more, and it looks like this. Symmetries of a pentagon, and that's a unit circle. So this vertex is gamma, this one is gamma squared, gamma 3, and gamma 4. So now let's find out what is the character of this representation. In our case, the conjugacy classes are the following. So we have here like this: CC of D4, so of course the first conjugacy class is of 1, and then it is easy to notice that the second conjugacy class is gamma and 4, because they are like conjugate, and kappa takes conjugates, you see, kappa gamma is equal gamma 4 kappa. So look what happens if you take gamma. So kappa, gamma, kappa is equal to what? This is exactly gamma 4. So these two elements are conjugated. And then also we have here gamma squared and gamma 3 by the same reason. So those are the conjugacy classes of first rotation trivial, second gamma, third one is gamma, and then of course you have here the reflection. So the conjugacy class here, maybe I should use different bracket. I should write it down. Okay, I just keep it like it is. Kappa, this is kappa, gamma kappa, gamma squared kappa, gamma 3 kappa, and gamma 4 kappa. And let's check it. So what happens if I have here, take kappa and take gamma, gamma 4. So what do I get? I'm getting gamma squared kappa. So we know that this one, gamma squared kappa, belongs to kappa, to the class of kappa. So now I take the next one. So what about if I made a mistake. Sorry. Correct. Maybe I should. I'm sorry, but it has to be corrected. I cannot tolerate something which is using the incorrect notations. Correct notations has to be used, because here I'm indicating, first of all, the conjugacy classes. So this means simply that we have here not this is the wrong notation. I should write it down. Set composed of this element. Then I have set composed of this element. That's a conjugacy class. This is conjugacy class 1. This is conjugacy class of gamma. And then I have gamma squared and gamma 3. and this one is gamma square. And then I have here conjugacy class kappa, gamma square kappa, gamma cube kappa, and gamma 4 kappa, the set, which is in our case the conjugacy class of kappa. And now, as I indicated, I have here that gamma kappa gamma minus 1, which is equal gamma kappa gamma 4, which is equal to gamma square kappa. That implies that gamma square kappa belongs to kappa, to the class of kappa. Then I take this square and let's say like this, take this one square kappa, and I put here another one minus 2, which is equal gamma square kappa, and that one is equal gamma cube, and that one is giving me gamma, one second, gamma 4 kappa, and that implies that this is gamma 4 kappa belongs to kappa. And now take a gamma cube k, gamma 2, minus 3, do it correctly, gamma minus 2, so this is gamma cube, kappa, gamma 3, so this one we are getting here, it is equal 2, so this is gamma 5, minus 1 gamma 4, and this is gamma square, very good. Here it's minus 1, minus 2, 2 is this one, so this is 3, this was here, I'm getting minus 2, and I'm getting 4, and very good, okay, so this is equal kappa, and now 4, let's do the 4. And this one is equal gamma 4, and this is kappa, this is gamma 8 kappa. And what is gamma 8? Gamma 8 is gamma cube kappa. Okay, gamma cube kappa. I am not so sure that this one is correct. This one is maybe not correct. Let me check it. Gamma, oh, yes, this is minus 3. Sorry, this is minus 3. Yeah. So this is 2, and this one is going 3, so I'm getting here, this is incorrect. This is going to be gamma 6 kappa, and that one is equal gamma kappa, and we got all of them. 1, 2, 3, 4, and kappa is there, so all of them belong here. So we are getting gamma kappa belongs to k, and gamma cube kappa belongs to, not correct writing, gamma cube kappa also belongs to kappa. So we got it. So let's compute the character of this representation. So character of this representation is a function, so let's say what kind of function it is. So we have here, this is my representation, so this will be 1, this will be gamma, the third one is gamma square, and the fourth one is kappa. And here we have the values of the character. So this is the trace of a matrix. So put it like this, and this will be G. So this is my V, and this is value of kappa on G. So you take value on 1, so that means this will be V on 1. Not good. Sorry. So we have to be improved. So put it like this: gamma, more space, gamma square, and the last one is kappa. And here we have here G of V of G. So this will be first one I take, and this one is equal to 1. And that one is that one, and that one is rotation. So gamma is basically rotation. You have to understand what is the rotation in our case. So this will be phi, and we have to take here at the gamma square, and finally we are getting here that this one is on kappa. So what is this value? So we notice that t, write it down, t of 1 is identity. So this is the identity operator. So of course, if this is identity, so that means the matrix looks like this, 1, 1, 0, 0. So clearly we are obtaining that the trace of this matrix is 2. Let's go do the rotation. The rotation by the angle, in our case, theta is equal to, maybe make it in red. So we have here theta, go down, theta is of our rotation is 2 pi over 5. So the rotation gamma is nothing else than, okay, this is cosine. So it will be like this, cosine theta. And this one will be, minus sine theta. And that one will be, and this one will be cosine, sorry, sine theta, and this one will be cosine theta. Cosine theta. This is the rotation. And so what do I get here? I'm getting here that the trace of that one, this is a real matrix, remember this is a real matrix. So in this case, the trace, so we are getting kappa, and V on gamma is equal 2 times cosine theta, which is equal to 2 times cosine. Okay, so how many degrees it is? How many is this? 72 degrees. I believe this one is cosine 72. So this will be square root of 5 plus 1. Am I right? Am I right? I think so. So 4 by 2. I hope so. So this is square root of 5 plus 1 over 2. And similarly, let's do the next one. So what do I get here? I'm getting here that for gamma square, we are getting the matrix, it is equal to, again, that's cosine square, cosine. So this is 2 theta minus sine 2 theta. This is sine 2 theta, and this one is equal to 2, and that one is equal cosine 2 theta. So where is this cosine 2 theta? Cosine 2 theta is here. So what is the cosine of this one? The cosine is that one. So I believe this one is, this is true. Similarly, we are obtaining that one is 5 minus 1 over 2. And finally, for the last one, if you take the kappa, you see the kappa is 1 minus 1, 0, 0. Minus 1, 0, 0. So the trace of this matrix, so let's write it down, is of kappa is 0. So let me check, this one is 0. Okay. I hope it is correct, but since I'm not trusting myself, I can always go, and why do we have computers? So let's check it. Gap. So we have a gap. I don't need any packages here. I just simply, maybe let's say load. And here I will always use, so we will be using it. So this is EquiDeg, and that one is package. So I have to return load package. Is it correct? Check it. Yes, and now put here G is equal p the group 5. Wow, we got it. So now I have here conjugacy classes. So CC is maybe small CC is equal conjugacy classes, and then we have here conjugacy classes of G. Check it. We have it. So you can see that first one is trivial, second one is kappa, third one is gamma, and fourth one is gamma squared. Now we can write it down. Irreducible representation, so put it like this, and let's find all irreducible representations of that one, and let's see which one is the character that we are talking about. And I can see there are two of them. Yeah. Oh, interesting. It's not really showing. Maybe, yeah, maybe you can see here that the two characters could be those ones, one of those. Okay, good. So let me indicate what we have here. Okay, here we have 72 degrees. So what's cosine of 72 degrees? I'm just checking if this is correct. Cosine of 72 degrees. Yeah. And that one is 72. This one is 36. I'm not so sure if it's correct, so let me. So no, this is 72. No, that's not true. This is 72. This is 180 or minus 144. This is 6. And this one is 30. Good, very good. And let's check it. So while we have computers, let's check it. Okay, let's do it. So this is alpha, Wolfram. And we have alpha, and we ask the question. Cosine 72. Cosine 72. 1/4. Yes, we concrete. So we know that this was not correct. So let me go to my table. Yes. And I'm so sorry. I was not confident today. So that one is definitely put it like this. Minus. This must be minus. Very good. And what is the 36? 36 plus. Okay, vice versa. Plus. So good. Good. Okay, so I'm now okay. I didn't lie. I checked myself. I showed you how to find these representations, and now we can even recognize them somehow. Okay, so there it is. So what are the other properties of the character? So we notice one thing, that if you take the trace of identity matrix, the trace of identity matrix is dimension of V. Dimension. So this is the dimension of the representation. So we can simply say simply say the following. So this is number 2, or how do I denote it? My first property is 1. So call this property number 2. So if you have a character of the representation, and E is the neutral element of G, so this will be the dimension of V. Dimension of V. Very good. So, moreover, notice that if you have a trace and you have here A plus B, two matrices like that. So one matrix is like a block matrix A and B. This is 0, 0. So the trace of this matrix here, this will be trace of this matrix plus trace of this matrix. So this will be trace of A plus trace of B. And immediately we are getting the next property, number 3, that if you have two representations and you take their direct sum, or if you have a representation which has two components, V and W, so of course this will be equal to the sum of the two characters of one of V and second one character of W. So it's a character of W. So those are the obvious ones. The one that is more difficult, and I'm not going to prove it, that's why we have to go and find some time to study the representation theory, at least elementary one. You have the following: if, so maybe write this without if, 2 G representations V and W are equivalent if and only if their characters are equal, identically exactly the same. So this is the way how we can recognize the representation just by looking at their characters. And let me return to our problems of the degrees that we were talking about, especially the formula that we derived for the computations of the G equivariant degree of the linear map. In this case, we had that we need to construct the list of all irreducible G representations. So, in the case, for example, pull it A, G is a finite group. In such a case, we can use our program GAP that I just was running, GAP, in order to create such a list. Let's see. I just did it. Look, I just ran this. I constructed. So the command to find all the irreducible representations is exactly that one. And this is irreducible representation of G. So then, since this is let's say a character of representation, as you notice, is a vector. Here is a 4 vector, has a 4 coordinates, 1, 2, 3, 4. First coordinate is the dimension of the representation. Second, third, and fourth are just describing the other possible values. So now if you look at this representation that we have here, so let me write it down, try to figure it out. Yes, this is maybe like, let's say like this. Let's look at that one and say like this. Number 1. So what is my first representation? So in my first representation, you are getting here, yes, this is the vector here. You can see this vector here. This is 1, 1, 1. What possibly could be what possibly could be this representation? You can see immediately that in such a case, put it like this. If R is the trivial representation of G, so what does it mean, trivial representation? There is no action. There is no action. That means G of X is equal to X. So every element of G acts like identity. So since we know that if identity acts like a identity, then we are getting the dimension of the space. So in our case, we are getting here that this must be the trivial representation. So R is a trivial representation 10. The character of such a representation 3. So put here V. Such a representation is exactly the matrix which is 1, 1, 1 everywhere. So this is trivial. And we denote this trivial representation as a V0. However, in our case, since we are using gap, and gap is numbering this representation, so it is actually our irreducible representation, call it like this, small I, irreducible number 1. So sometimes it is convenient to use 0, so you understand this is exactly the representation that is supposed to be trivial. Or you can just simply use the gap numeration instead of 0, just write 1 and also remember. That's your trivial representation. So usually the trivial representation is first representation that appears in this list. Then it appears in this. Of course, if you want to check other representations, irreducible representation of this group, so you check the number 2. So I'm getting here, oh, this looks also one-dimensional, and now on the, you have here one-dimensional representation, and then you see that the function so we have here this vector which is like this 1, minus 1, and this one is 1 and 1. And notice this one, as I remember, this is kappa, this is gamma, this one is gamma square, and this one is 1. So what possibly is this representation? What kind of the action is one-dimensional, and how there is the action? What is the action on R? So you look here. Kappa is a rotation. So rotation acts by all rotation acts by multiplication by minus 1, and gamma squared just simply act as identity. So in such a case, it is easy to note to find out that this action. So in this case, if you take Gx, it will be equal x if G rotation, and this will be minus x if G reflection. And that means T goes from D5 to O2, which is O1, so which is Z2. So this is equal to Z2. So we are getting here that kernel of T is exactly equal Z5. So that's this representation. And then we can play like that and look like, let's say like this. Let's see which possibly could be our representation, And yeah, I cannot recognize easily from this case how to recognize it, because that's exactly this 2. That's a number. So put it like this. Here, 3. You can see in this case. I don't know which one is this root. So I need to educate myself. I'm not so good in finding out what these numbers are. E5. what it could be. So let me educate myself, and then maybe we will return to this topic. So okay, so we have in certain way created a system, let's say, that we can use the characters to recognize the irreducible representations. And now, of course, if I have these irreducible representations, the first thing that comes to your mind is this possible? Is this possible to let's say, to find the basic degrees? What about the basic degrees of these representations? Degrees. So we have here like this, we have here V0, so this will be R number 1. Then you have here V1 is irreducible number 2. And then you have here V2 is irreducible number 3. And then V4 is irreducible number, so this is 1, 2, 3, 4. So this is 0, 1, 2, and this one is 3. So those are our representations, And let's compute the basic degrees. So maybe, first thing, remember we have something which is called I would say like this, put it like this. Basic, so start with the first one, basic degree, so deg number 1. Double. I hope it is correct. No, maybe basic degree. I'm correct. I'm just. Oh, I don't need. You see, this is all because of my lack of experience using. So in order to get basic degrees of this representation, you're exactly getting you're writing basic degree and compute it and apply it to the character. So basic degrees can be computed from the characters. So basic degree. So maybe I denoted basic degree because this is for trivial representation. Call it 0. Very good. And maybe remember we have here conjugacy classes CCS. So this is conjugacy. Conjugacy class misspell. Conjugacy classes subgroups G. Yes, got it. So now CCS 4. What is 4? And you can recognize what is 4. Ah, conjugacy 4 is exactly the whole group. So there is a whole group. Let me write it. So we have here like this. Basic degree, so put it like this, degree of the V0 is equal minus D4. I just computed my first basic degree using the trivial, let's say our package for graph. So if this is done, then let's compute the second one. And now I put here like this. Number 2. Sorry. Go back, put here 2. Ah, I'm getting the second one. So what is the conjugacy class of CCS number 3? Because we need to identify. What is it? This is a Z5. Those are the rotations. Very good. I just computed the degree of the second one is equal. This is 4 is D4. So this is D5. I'm sorry, D5. And this will be minus Z5. So this is D5 minus Z5. Now let's go to the number 3 and number 2 and degree number 3. So let's do it. 3. Maybe. Mess. V3, 1, 1. So let's do it. I'll just go here and write it down number 3. There is a 2 and 1. 1 is trivial. So CCS1, we are getting here. This is trivial group, CCS2. And you see this is kappa. So this is D1. D1 and trivial. So the number 3 is equal D5 is this 1? Let me check it. I don't remember. 2. So this is 2. D1. This is D1. So this is 2 times D1 plus Z1. Very good. So let's go and finish the list. And it's going to be number 4. Number 4. And I look at this and what do I see? I see this is exactly the same degree. So doesn't really matter. We didn't recognize this, this particular representation from the point of view, like is it this exactly the one that we were discussing in our example, or maybe this another, but we noticed the degree is exactly the same as in the previous one. So that means in certain way it is not so important. So this is exactly the same, but we can write it down in both cases. This is D1 plus Z1. So that's how this is computed. This is how it is computed. And okay. Maybe let's go further and let's consider the product. So in the case our group G is equal to the product, let's say gamma 1 times gamma 2. And we know and we have the lists of irreducible representation representations for for gamma 1 and gamma 2. No, this is not nice. Gamma 1 and gamma 2. And what is our list? So let's write it down. So here we have the list. So those are Vj. And those, let's call them Wk. Wk. So in such a case, what are the representations, G representations? Of G. So G representations. So irreducible, maybe. What are the irreducible G representations? And in this case, it is kind of easy because we can denote a J, comma K, and this will be just simply Vj tensor product, and this will be K. So the tensor product of the gamma 1 representations times gamma 2 representation will be our irreducible representation here, but it will be our irreducible representation for that group. We will be using this notation in the case when we will be studying the representation of the groups of the type. So we will use this notations with the two particular, with the two. We'll write it down like this. This is V. We will the two indices like J and K in the case when our group G is equal gamma times O2. So first of all, here gamma is finite. And in this case, since gamma is finite, we have here, we can use gap to obtain the full list, complete list of the irreducible representations. Full list, it will be Vj. But in the case of the O2, which is clearly an infinite group, we have infinitely many, the following: irreducible, G, so means O2 representations. Yes, O2 representations, namely, so let me write. So of course we have here W0, which is trivial. So this is trivial. And then we have here W, and I put here K. In this case, it will be R2. K is larger than 0. 0. And this can be considered a seat, and we have here O2. You have here two types of EI theta. So those are the rotations. And we have here EI theta kappa. Those are reflections. And of course, kappa, in our case, how this EI theta acts on Z from C. So this will be EI, and I put here theta. Maybe clearly I should use K. You see K put here. And this will be theta times Z. And that one is complex multiplication. Complex multiplication. So the rotations act by this, we call it K-folded action, because folding, if you notice what happens to the circle when you apply this transformation, take a point from the circle, take it to the power K, complex power, in complex sense, then you will get that this is becoming like a K times wind it around. So you wind this circle K times around itself. So in such a case, we just think about this as a folding, because if you look from the circle to the top, you will find it like the circle is folding like this. So like that. So you have circles folds like this K times, and then you map it here. So this is this map Z, and this is Z to the power K. So this is like a folding. So K folding. So that's this one. But that's not all. There is one more, but we already used all the indices. We used all the indices, so how to denote the one more representation? So in such a case, since we run out of all the indices, sometimes it is appropriate maybe to use different symbols, but why not to write it down like that? There is like a -1 representation. -1, which will be in our case R. So this is additional, so this is one-dimensional. And the same as it was in the case of the dihedral group D5, if you have your reflection, so you put it like this, if you take the reflection EI theta acts on X, this will be just X, and kappa on X will be minus X. So reflections act like minus identity, and the rotations as identity. So this is also one dimensional. So in such a case, it is convenient, it is kind of a convenient to use this notation that the representations of the gamma times O2 will be just simply JK, which will be representation J tensor product of representation K. And then what we need to do, we need to go back and illustrate some more examples using GAMP program, and I'll try to prepare myself better because I'm not very skillful, as you notice, with the computers. It's much better to have everything scripted in advance, so I can just copy and paste. Otherwise, I will be making too many typos typing these things. So I will be back in a moment. So this is our first example. We'll be doing the group D5. So let me put it on D5 times example number 1. Example, and this is 1, and this will be group which is equal D5 times Z2. So where is my script? So let me go to gap, and I will close the gap, so we will start it fresh, and then let's go to the script, and you see, so what we are going to do, we'll restart the gap, load the package, then define the dihedral group D5, dihedral group, let's say symmetric group Z2 is nothing else than Z2, so this is symmetric group 2 is Z2, and then we create the product, get the conjugacy classes of subgroups, give them the names, we recognize them, give them the names, and then associate these names with these conjugacy classes. Then we take the let's say we find the list of all irreducible representations by identifying their characters, and then we'll compute some, not all, of the basic degrees, some of all of those basic degrees. So let me do it. So let's start the gap. So we're starting the gap. Yes, we have here. Now we go and let's just copy it. So I just copy it. Let me do it like okay, the group. First portion first. First portion. So we go here. Open. How to copy it? Did I copy it correctly? No. Problems with copy. So again, Control C. And then we go here and we did it. So we have the group and enter. So I have the group. The next thing is the conjugacy classes giving the names. So let's do it. Control C. And then we go here and do the click. Oh, it's done. And set the names. The names are set. So remember we have CCS. So now I will check how it works. So CCS1. Do I need to do anything here? Yeah, it already gives the names. So maybe CCS like 10 or 11. Oh, I think I went out of the 9. Yes, D5Z. Yes, it is giving the names. We already discussed the conventions, how it is that we are using here, the so-called twisted notation for the subgroups of D5 times Z, Z2, and what is happening? Maybe let's say size CCS, how many? 10, yes. 9. Yeah, it works. Sorry, I just pressed something unintentionally. Something unintentionally. Okay, so it works. So now, once we have it, we will get the irreducible representation. So we copy it again, and we paste it, and we'll find out how many of those representations we have. How many we have here, let's say. Enter, and maybe size, again, size. So how many in our list? So I, R, 8, we have 8 irreducible representations. So okay, let's compute some of them. So not all of them, but some of them. So Control C, and now I'm going to V. Sorry, I have to this one. Oh, yes. Enter. So we have degree 1. I guess this is minus the group G, and this is group G minus something. I forgot what is 9. So I think we just did it here. We just did it just around here. It was the, look, this was the D5Z. D5Z, 9 is D5Z. So if you don't remember, like you don't know what 8 means, it is easy to just simply write in a CCS, you put here 8, and since we have the associated the names, it gives you D5. So you can just simply say that this DEG 5 is simply equal to, so no, this is DEG 3 is equal to, what is the DEG 3? Like degree of V3, that's it, 3 is equal D5 times Z2 minus D5. D5, right? So this is the of course, if you have degrees, those are elements of the Bernstein ring. Why don't we multiply just degree? Let's multiply degree 3 by degree 8. So degree 8. Let's see what happens. Those are the elements of the Bernstein ring. Multiplication. Yeah. So let it slow. Yeah, and we got the product. We got the product. If you want to know exactly what the group is, just simply write CCS and 1, 2, 3, 5, 8, 10, and you will know exactly what it is. Okay, so that's my first example. This is my first example. Let's go and do the second example. So in order to start it fresh, I just quit, and we'll start it again once we choose the group. So what is my next group? My next group looks a little more complicated. So this is D3 times D3 times Z2. So let's write example 2. And the group is G is equal D3 times D3 times Z2, and that's it. So this is our group. So let me look at the script. So let's start the gap again. Let's start it, gap, and let's introduce this group into the gap. So let's go on this. Let's look at the script. So where's my script? And that's not the one. Let me close it. Oh, here. This is the script. So let me just simply discuss quickly. So first one, we load the package, and then we defined the group D3, and then we define the product D3 times Z2, and then finally we define the group G, which is the group that I mentioned. Then, of course, we generate the subgroup, conjugacy classes in first, let's say, first factor of the group, second factor of the group, and then the conjugacy classes in the group G. Okay, let's do it, and then let's see what happens. And then we have that one. So let's do it. Done, and then enter final line, and we have it. So for example, let's see what is the conjugacy class CCS, and this will be 45. And if I put it like this, it gives you the generators. It is kind of a, let's say, not obvious from the first look what kind of the group it is. You would like to have the amalgamated notation in order to decode this subgroup from the point of view what kind of the action it is. So let's introduce the symbols. Here we are using the symbols which are known, let's say, in the product D3 times Z2, which we describe as the so-called twisted symbols. So they were discussed in my previous lectures. So in this case, let me do it, let's say enter, we have the symbols, and now of course I want to know again what is this CCS45, so that's why I'm writing amalgamation now. Symbol, did I write it correctly? And then I have open bracket, this is CCS45, close, close, close. If I have no typos, then it will work. And we are getting it. Yes, this is the amalgamation symbol. And I can write it down here. So this is D1, and D1, and this will be D3. Good. So this looks like this. So this CCS45 actually is the group, is the conjugacy classes, which looks like this D1 times this is Z2 here, and this one is D3, and this one is D3P. D3P, and remember D3P is just simply D3 times Z2. Okay, so we have these symbols decoded. So let's continue, and let's find the irreducible representation. So first of all, let me find out what are the conjugacy classes of the subgroups in G. So let me copy it, and let's look at this list of these conjugacy classes. So I will just simply paste it here. Let's paste it and enter, and we have here conjugacy classes. And that's how many. This is size, and CC, sorry. So it is 18 such classes, 18. And let me point out that the 7, 8, I think this is related to the group Z2. So that means this is it. This one is identity, this is 1, and this is -1. And here we have 5, 6. Looks like 1, 2, 3, 4, 5, 6. So this looks like a kappa in the second D3 copies of D3. So if you analyze a little all those elements, you can definitely describe their let's say relations with this product. So let me write it down again. What do I mean? So usually in this case, if you have here D3 times D3, to remember, just associate with 1 plus 1 minus 1. So if you have here 2 copies of D3, I usually write it down like that. So you have here D3 number 1 is generated by gamma 1 and kappa 1, and the second copy of D3 is generated by gamma 2, kappa 2. So those are the 1 and 2 rotations and 1 and 2 reflections. In such a case, if you look at that that one, so you can recognize, for example, that first is just 1, so first is second, so it means simply you will notice that the first is 1, second one is minus 1. Then you have here, let's say what is the next one, so the next one is 5, 6, so this is kappa 2. So this is kappa 2, so this will be plus minus kappa 2. And then you go and you do similar identification. So here you see this is 4, 5, 6, so that's a rotation. This is the rotation in the second copy of D3. So let me write it down. This will be plus minus gamma 2. And then let's go further, and then you go and you see, oh, this is 2 and 3, that's kappa 1, clearly, kappa 1. So you are getting plus minus kappa 1. Yes, always will be plus minus. Yes, and then this is plus, and this one is minus. You see this is minus 1. So next one, sorry, 2, 3, this was 2, 3. And that one is 2, 3, 5, 6. What could be 2, 3, and 5, 6? Okay, in such a case, you identify this is plus minus kappa 1, kappa 2. And then go to the next one, and you can do all of them like that. You can do all of them like this. So you go to the next one, and you are getting here, this is kappa 1, gamma 2. So the next one is plus minus kappa 1, gamma 2. So those are the representatives of the conjugacy classes. And there are how many of them? There are 18 of them, so that means we need to list 9 here, because I'm putting all of them in the way plus minus, plus minus. So 1, 2, 3, 4, 5, 6. Of course, I need to put 3 more like that, and you will get the full list. So that's how we do it. So those are the elements. So now, of course, if I look at the representations, what do I see here? Let's say I write it down. Let me the list. I need to create the list of all irreducible representations. So let's do this list, irreducible representations list. So let me do it here and put it V. Sorry. Oh, I need to copy it. Sorry. Yes, we got it. Oh yes, I have the list. And now you can see, so pick up anyone, so you will count the numbers. So this is your vectors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16, 17, 18. 18 elements. You see, those are the vectors. As you see, there is no plus minus 1. You can say in this representation Z2 acts trivially. And then you can go further. For example, here you have 2 minus 2. So here Z2 acts non-trivially. And similarly, you look at all of them, and you can recognize this representation is of dimension 2, this dimension 2, this dimension 2, and none of them are dimension 2. Look here, it is couple of them which are dimension 4 and dimension 4. One has a trivial action of Z2, another one has a non-trivial action of Z2. It is interesting. What do you think? Which one is this representation? Which one is it? So it is not difficult to see. We have here one, let's say, one two-dimensional representation for D3. Namely, we have here this representation which we call D1. So this is C. This is natural representation of D1. We have it acts by rotation. So in this case, you can see that in the first one, we have so we have here for the first group is D1, and for the second group we put it like this. So maybe I use the notation like we used before in the present. So this is my first component. So this is D3 times D3 times Z2. So that's my V1, and for that one, for this group, this will be again W1. Or again, this will be like a C. But here we have the action of Z2, which is by multiplication by minus 1. So if you have here multiplication by minus 1, and then you have similar representation 1, but with plus, that means there is no multiplication by Z2. So this is still C. So you can see that in our case, if I look at our list, which contains how many? By the way, how many here? So here, size. Say like this, size and this was ir list 18. Well, did you notice this is the same number as the number of conjugacy classes? So that's interesting. We'll remember about it. And in this case, that means the representation number 18 on this list, 18. So we have here like this 18 representation. So put it like this, 18. Our representation 18, so call it like this, U18, because I already used V and W. So that will be like a V1 times, and this is W1 minus. That's this representation. As you see, it is always possible, just by careful analysis of these representations, to recognize what they actually standing for. What kind of a representation it is. Just we look at them and can figure it out. And that's this moment basically it's kind of interesting. So I would say like this. Suppose we have a different representation. Suppose I have here, let's say, a representation like that. I take 3 copies of R3. 3 copies of R3. And on each R3, which write it down, this will be my new representation. I will write it down like this. I have here the set of x1, y1, and z1. So maybe write it down like this. No one, just simply x, y, z. So those are the elements from R. And now I can define the action of the first group D3. So remember, we have here D3 times Z2. So how this D3 acts, so I take here the generator, the rotation, and rotation will just permute these coordinates. So I write it down. So this x goes to, so this will be y, z, and x. And the kappa will act similarly. So if you look how this looks, so I say like this, x and y. I switch x and y, so this will be, no, maybe leave x alone and switch y and z, so this will be z and y. Sorry. Y and z, so this will be x and z and y. So I have the first action, so this is this copy, number 1, number R. And how the number 2 acts? The number 2 acts on the big one, on the V. So we have here actions, so let's say, so this is on every of those R3, the first copy of Z3 acts simultaneously. This is like a diagonal. So you can see that here, if you apply G from the first copy of G3, so it will be like this. Maybe I should be more precise. So simply let's write it down. This is vector 1. We have all 3 vectors. So we have here vector V, which is equal V1, V2, V3, and this belongs to this R3 times R3 times R3. So the first copy of, so this is the first copy of D3. So this is D3 number 1. So this is number 1. It will act like this. So you have G on V will act G on V1, G on V2. And this will be G on V3. So the same action. So it will just permute the coordinates in this vector. And this action is actually here. Here. That one. Easy. So now, what about the second copy? The second copy. So this will be another D3. For a moment without Z2. So I will just simply number 2 of D3. It will act. So if you take this another element, so this G belongs to the second copy of D3. So it will take G acting on V1, V2, V3. So it will be, for example, so let me write it down. Rotation. So we have here rotation. So this is my rotation 1. This is reflection 1. Then you have here rotation. So you have, if G is equal to rotation number 2, then this will be rotation number 2 on V1, V2, V3 will be just simply V2, V3, and V1. Similarly, but now it is rotating 3 by 3 vectors, 3 by 3 vectors. And of course, so plus minus 1 acts on these vectors V1, V2, V3, just simply as plus minus V1, plus minus V2, plus minus V3. So we have the very nice action here described, very nice action. So so of course it is possible to compute the trace of these actions, of this each of these each of these actions is a permutation of coordinates. Let's see. So where are our conjugacy classes? So okay, so this is plus kappa 2 kappa. So this is something like this. We have here plus minus 1. Then we have here plus minus kappa 2, plus minus gamma 2. And next one is what? Next one is plus minus. So plus minus kappa 2, gamma 2, kappa 2, gamma 2. And this one will be plus minus kappa 1, plus minus kappa 1, kappa 2, etc. So let's compute character of this representation. Let's compute character of representation. So the first one gives you the dimensions. So of course the dimension, and then if you multiply the entries by minus 1, it will be plus and minus 9. So what about the kappa 2? So kappa 2 actually is doing the following. Look, kappa 2, where is my kappa 2? Here. Kappa 2, let's write it down, kappa 2 on V1, V2, V3 is equal V1, and this one is V3, V2. So you can see clearly that here there is an invariant vector. This invariant vector is three-dimensional. So that means on this portion of this matrix there is a block, 3 by 3 block with all identities standing on the diagonal. On the other hand, the other two blocks are permuted, it's interchanged. So there is nothing, there are zeros on farther or zeros. So the trace of K2 is definitely 3, so I'm getting here plus minus 3. What about the gamma 2? What about the gamma 2? If you move, let's say, if you see, you rotate it, if you rotate each of the coordinates, if you rotate each of coordinates, so what is the trace of this metric? So in this case, you look, what is this rotation meaning? So you have here 0, 1, 0, this is 0, 0, 1, and this is 1, 0, 0, and you look at this matrix, say, oh, this matrix has clearly traced 0, so you can write it down, that one is 0. That one is 0. Very nice. Once I have it, actually, I can go farther and check out. Okay, let's check one. So one more. That one for this two. So in this case, if you look at that one, you can easily recognize this will be plus minus 1, and for the all remaining, it will be 0, 0, 0. So it will be 9, 0. So this will be 9 vector. And now I have this representation. I have the vector. So I would like to know what is the isotypic decomposition of this representation. Isotypic decomposition. And I can do it. Can you imagine? We can do it very easily. Namely, let me do it. So first of all, I already know what this vector, so put it like this. This vector is equal, and I have the coordinates. So first is 9 minus 9, 18 coordinates. Then I have here 3 minus 3, 3 minus 3. Then I have here 0 and 0. Then I have here 1 minus 1. And then I have 8 zeros. So this is 1, 2, 3, 4, 5, 6, 7, 8. Am I right? 1, 2, 3, 4, 5, 6, 7, 8. 8. And this is my vector. This is my vector. Check it again. It's not correct. not correct. It is definitely screwed up. So let me do it again. 9, 9, 9, 1, 2, 3, 4, 5, 6. And now I will find the isotypical decomposition. How do I find the isotypical decomposition? So namely, I know that my irreducible representation, so this is irreducible representation of G. This is a matrix, irreducible list. This is a matrix. You can think about this matrix. This is a matrix. And then you can say like this is my x1, this is my x, in our case 18. And this one is equal to our vector that we just computed. So this will be 9 minus 9, etc. So those are this matrix, those are the irreducible representations. So if you look at that matrix, this actually matrix is solving the equation x1, and you have here your first character, kappa 1. So this is x1 times first character, this is not kappa, this is theta 1, okay, eta 1. Then you have here the second character, etc., blah, 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 and this will be x18, and this is the last one, 18, is equal to your character, our character v. So that means that this number is showing how many copies of the first irreducible representation are there. This is the number of copies, then you say. Then I have here the second representation, how many copies of the second irreducible representation are in the representation V, etc. So this will definitely produce me the isotypical decomposition, provides me with the isotypical decomposition of this matrix. So let's do it. How, you see, explaining of what's really going on here is more difficult than actually solving the problem, because we can write simply like this: solution mat, and I put here like that. So what is this? Ir list, and I put here V, and I hope it works. I have to find out what I did. Probably I wrote something. Solution matrix. Did I write V? V is here. Okay. It is a matrix. So, okay, so why it is not working? Solution matrix. Let's read it again. Oh, it didn't work. Did not work. So I'm sorry. It worked before. This is a new version. Doesn't work now. Cool. We have to figure it out how to convert this matrix to the regular matrix. It will basically, you need to do it yourself. I don't know it. I have to educate myself. Before it worked now, I think I'm abusing the program, because program is recognizing that this is not ordinary matrix, this is character matrix. So probably that's why I'm not getting what I want. Anyway, let's continue. Let's continue and let's do more computation. So you see, oh, actually you have here these things. Let me do it. Maybe I do it again. Copy, and let's see. Maybe I just did a mistake, like forgot a 0 or something like that. Let's see. Yeah, I think I just copied something wrong. Now it is working. I'm getting a solution. So you can see clearly that this is my representation 0. So the component 1 has 0 first. So 0 representation 0, 0, 0, 10, 1, 2, 3, 4, 5 has 1 V5 representation in isotypical components 5. This is 6, 7, 8, 9, 10. 10 has also 1. Then you have 1, 2, 3, 4. So you have here 14 is one dimension, and final is 18 is one component there. So we just found the isotypical components of this representation. So this example actually works. So let's compute the basic degrees and maybe look at what's happening here. I will just compute a couple of these basic degrees, and you can actually multiply them as well. So I don't want to, yes, so this is, let's copy, let's paste. No pasting. And this is not want to paste. Again, copy, paste. Where is it? Basic degrees. Control C. Again, paste. See how bad I am with these things. Again. Yeah, I computed several of them. 17, 9, etc. Nice. So let's do the following. Multiply some of this. So take a degree. 17 times, which one computed? 13 times degree, 13, and let's see what happens. Can we compute? Yeah, it's computed. It's kind of a long. So you have here, wow, all this, you see, this is the result. This is result. You can figure it out what it is. Okay, so I'm not going to continue this example. I'll just go to the next one, and let's do the, so this is quit because we go to the next example. I wanted to first the group O2. Where is my O2? Z2 times O2, but since we wasted the time on the on this representation, that probably I forgot a 0 in the character or something like that. That did not work. So it's my fault. I wasted the time. So let's generate the group which will be of that type. So this will be S4 times Z2 times O2. So my next example is S4 times Z2. This is my first, and the second one is O2. And now we remember how it works. So we'll be having the irreducible representations with the two indices. First one will be, put it like this, this will be J, and the second one will be K. This will be corresponding to the irreducible representations of O2. J will be corresponding to the irreducible representations of S4 times Z2. So let's do it. And where is my script? It is here. So we need to load the package. We give the names like we did before. I will include some of those, let's say at least 2 scripts in the description, so you should not worry about it. Then I put the product, and I have here the conjugacy classes, and this is basically it. So I have here display conjugacy classes, etc. Good. So we have character table, which is called the TBL. Okay, Control C, and let me run it. So gap, and we have it, the group. Oh, this computing the group, as you see, conjugacy classes in this group. It takes time. You see, it's kind of long. Did you notice? It is not so immediate. We are now becoming slowing down. we are becoming slower and slower. And I cannot push it. So maybe I go here and I just prepare my computations of the degree. We put, as you notice here, there. Maybe I should change it. So I'll just call it like it is 1, 3. This will be 2, 3. You see, this is something that I wrote earlier. I don't know why it is 0, 7. I will just keep it like it is 1, 7. Or like it. So it will be not so 0, 8. Those are my degrees. Control C. Let me check. Still computing. It's still computing, so I'm sorry. Oh, done. So now let's compute the degrees. First one. I made a big mistake. I didn't realize it's going to take so long time. So I'll try to shut. Oh, actually, it's not so long time. It's kind of a quicker. So you see, we have the first degree computed. Nice. The second degree is coming. So it gives us an idea how the program works, that these things are actually totally computable. We are getting these degrees and we are using them. Later, we'll be using them in equations. We'll be just solving, let's say, the problem of existence of the solutions to symmetric systems, and we will be interested in finding out what can we say about the solutions, symmetries of the solution set. That means, what are the solutions and what are their symmetries? Those are going to be our issue that we are going to address in this particular let's say in this course. That's our objective. So I'm just talking to kill the time. So maybe I'm not doing well. Maybe I'm just talking some kind of a nonsense. So I'm sorry. You should definitely forgive me, because you see, for me, using computers and actually we're using them seems like a kind of a challenge. Oh, I'm doing well for my age. I'm doing well. I'm not getting completely crushed by the technology. I can actually see something is showing up here. Yeah, there are some results. Good. And it is working. So I computed this. And I'm interested in that. That's interesting. How to get the amalgamated notation for these symbols, because they look kind of let's say 1, 107, okay, for example, 1 and 330. There are actually infinitely many of those groups. How can I know what is the symmetry? It's just kind of a symbol, and I do not know what it is standing for. It is important maybe to find out what the symbols is actually representing. Let me see. What is the notion for our conjugacy classes? So conjugacy classes, Z1, and then we have those are our conjugacy classes. It's not CCS. Now it is CCSs G, and that's exactly what we are doing. We are complicating our own life. In the previous examples, I was using CCS, and suddenly this is CCSs subscript G. Wow, it's getting confusing. It's getting confusing. Okay, so we wait for the last degree, and then we will find out what the symbols here stand for. what these symbols stand for. And we'll see. So it is possible to. Yeah, this degrees have many coefficients, so those are really kind of a elements of in the Bernstein ring, which would be kind of a, how to say it, desperate to try to compute by hand, like we were dealing before in our examples that I was trying to present. Maybe this one is not working because I don't need this one. Okay. Maybe. Let me check. Maybe it's not computing. No, it's computing. No, it's not computing. So yes. So let's remove it. So this is CCSs G, and we want to know what is this 1, 3, 3, 3. No, 3, 3, sorry, 3, 3, 3. This one, this element. And we have the amalgamated notation. Yes, this is the amalgamated notation. Very good. And what about the other one? What about the other one? 1, 0, no, maybe no, I want to. 1, 204. Why 204? Let's say, let's do it. Maybe 3, and I put here. Just check what would be happening if I take that one. 4 for 3. No, I think I overdid it. There are no 4s. Maybe I should write 100. I'm just playing. Oh yeah, works. Look, 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 it works, it works, it works. With this optimistic accent, I'm going to end this kind of exhausting lecture. Yeah. By the way, you can multiply these degrees. I tell you, I would not attempt to do it in this moment because once, some time ago, I was looking for this product, and it took me whole night to get the results. So there's a lot of computations there. So thank you.